Go for it. Okay, this is Zach Mitchell. We're doing our Physics 211 project.
This is Aiden Chavez.
I'm Tristan Powers.
So we're going to be starting with our acceleration graphs, position graphs, and velocity graphs, both in the x and y axis that we got from doing derivatives of the functions and antiderivatives to find out these areas and plugging in values to our known constants. So starting with the acceleration in the x-axis, we plugged in a value for big T of 4 and b for 2. And we know our limits of movement on this function are going to be -4 and 4 because of our t value. And with our acceleration in the x-axis, we see original positive movement starting at -4 going to 0, showing the helicopter's upward acceleration and growth. And then for a very brief moment, the acceleration sits at 0 and then slowly decelerates at the same rate back down to 4, where the helicopter will have landed on the ground, and these land between the bounds of our T4 and -4 values. Moving on to the velocity in the x-axis, it shows the helicopter rise up with position versus time, starting at -4 in our bounds, increasing all the way up to where the velocity reaches 0, where it sits at rest for a moment, and then slowly moves back down, coming back to a rest at -4 because of our bounds. And for both of these, if we took our t value and stretched it and made it larger because it is an unknown variable, and we just plugged it in, all that would happen is the graphs would stretch accordingly, and we would just cover more distance as we're in the air for longer. And our displacement in the x-axis, starting from -4 to 4, because we're using the same values, it shows how the helicopter starts down at 0 and then will accelerate, reaching when it crosses 10, it's going to be accelerating at its highest point. Then it will start to slow down as it comes to a landing as it approaches 4. And same thing as if we were to change our t value, the graph would just stretch and cover more ground as we have more time. The acceleration in our y-axis is shown a little differently. It looks kind of flat because most of the acceleration is happening in the actual x-axis, but it is still between the same amount of points, and we see some positive to negative acceleration upon takeoff, and then some positive back to negative acceleration upon landing. Our velocity in the y-axis is also similar to kind of how our acceleration is. It's more flat, as we only really see changes upon takeoff and landing, where we have some positive velocity on takeoff, where it then comes back to 0, as most of the velocity change is happening in the x-axis, where we also see some velocity change before landing. Displacement in the y-axis is actually where we get some interesting data, where -4 we start more as in like a crater. And then as the position in x is changing, not much is changing in y. And then as we come to a landing, we see that the helicopter ends up on a hill, hensing that it's not a perfectly flat surface and that we're landing a little higher than we began.
Okay, now for our sense making. So to start with, we have to assume that alpha and beta constants are going to be greater than 0, which would put them positive. Without the beta constant being positive, the helicopter would essentially just sink into the floor, and that's not what we want. We want to visualize the helicopter moving up. So the helicopter, in terms of x direction, the helicopter would accelerate in the positive x direction. Time would be greater than our negative capital T constant, and at t equals 0 for time. So once it hits 0, the acceleration would change its sign and it would increase in the negative direction. So this would be it descending down from its top point. So in the y direction, we have time would equal, again, given in the problem, this is our negative t constant. Acceleration is also in the positive y direction as the helicopter accelerates upward. So after our time constant is greater than or equal to our capital T, velocity would be in the negative y direction once again, as the helicopter again descends. So we found in our calculations that the final time is equal to 2 times the t constant that's given in the problem. And we did this by simply just plugging in values as shown in the graphs earlier. So we can go back and check the sign of the velocity and its direction. And that would be from our initial value, which is time is equal to the negative t constant, to time equals 0. And that's because acceleration was positive and our initial velocity in the y direction was, of course, 0.
Okay, now for the reflection, we're going to look at a problem that we found to be pretty similar to this problem, which is the Mario problem that we looked at during lecture. In both problems, we're given a known time constant, big T, and we're solving for the total displacement, or where the object has moved over a certain amount of time. In both problems, we find the antiderivatives from our initial equation that we have, so that we can find the graphs and equations for acceleration, velocity, and displacement. Because we determined that since we have a known acceleration of an object as a function of time, from there we can then solve for the velocity and this displacement by using our antiderivatives. One thing that was different about this problem when comparing it to the Mario problem is that we did break the components up into different x and y components, whereas we didn't do that in the Mario problem. Next, we're going to look at another problem that we found to be pretty similar to this one, which was the 3 marbles problem, where 3 marbles are rolled off a table at a certain height and also at different angles. The reason we found this similar because in this problem we did break the components up into x and y components, and then from there we could find like the different velocities depending on the angle. In this problem we're also solving for the displacement in the x-axis, so that the distance that the object has moved from the initial time, as well as the time spent in the air from rolling off the table, or in this case, taking off to landing.
Sweet, and that's it.